coming. So we get something that says 0 divided by 0. Technically, it's not undefined. It's what we call indeterminate. Okay? So we can't get a limit of that either. So whether it was 0 dividing by 0 and undefined, or we got this indeterminate thing, we still need to be able to have some other things to do. The other thing that's indeterminate that you'll see, not quite yet, but soon, is you might see an infinity over infinity. That's also what we call indeterminate. Okay? So we saw these two things yesterday, so it's kind of like summarizing what we saw yesterday. You can divide out like factors. That is the factoring. Okay? And then you can rationalize the numerator, which we saw that in yesterday's part of the lesson. Okay? So today what we're going to do is another thing that can help us if we have something that's possibly indeterminate. Likely you won't, I've already got scribbles here. Likely you won't, likely it'll probably already be set up for you on these, but just in case it's not, this is another way to deal with an indeterminate. You can't get it to do all the other things we already know. Okay? So this is the squeeze theorem. It is part of, like, I have to follow a course description for AP, and it's very detailed in what we're supposed to teach. So sometimes I'll skip things that a normal college class might do because it's not part of AP. Okay? I sometimes will, sometimes doesn't. So this is one of those things where they tell us that we got to teach it, so it is fair, 100% fair game for the AP test. The amount of times I've seen it in the last 10 years I've been teaching AP, it's very, 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 very few. Okay, that doesn't mean it couldn't be there. Right? So I'm going to teach it. The book is very, very thin on this type of problem. Literally, I copied one. Okay, that was reasonable to do. So you're going to try the one problem. Okay, we're going to do 3 examples, so you've at least seen a few of them. You've seen them in slightly different situations, and there's one that has some interesting outcome. So here's what the squeeze theorem is. Notice they say you've got 3 different functions, right? You've got a little function, you've got a big function, right? That's what the inequality signs mean. And you've got a function that's squeezed in between them. That's why it's called the squeeze theorem. It's in between. Okay? They basically have the same open interval that contains C, except maybe C itself. So what that means is there might be a hole at C. Okay? So that's but everywhere else is the same domain, basically. Okay? So you'll notice that this f function in the picture's kind of nice. It's something crazy, probably something that we don't know how to figure out the equation for. So sometimes it's difficult to find a limit of some of these crazy functions. So if we find a function that is smaller than it, that we recognize, that looks like a pretty good parabola, right? Which we know how to find the limit of a parabola, we can do that by direct substitution. Okay? And we find a function that is bigger than it, that looks like a parabola too. We can probably plug in direct substitution. So if we can find those 2 limits of the smaller function and the bigger function, and if those limits are equal, it would only make sense that the function that's squeezed in between them would also have that same limit. Okay? So basically we're trying to find the limit of the smaller function, the limit of the bigger function. If they match, the function squeezed in between has that limit. Okay? That's the squeeze limit. We're going to try that. In this one here, they gave us the 2 functions that are being squeezed. They really didn't tell us what the middle function was. This is kind of similar to what so they want us to evaluate the limit as x approaches 1. So here's how I'm going to set it up. So we're going to start right. Limit as x approaches 1 of 3x. And we know that's supposed to be less than the limit as x approaches 1 of f of x. And that's supposed to be less than the limit as x approaches 1 of x cubed plus 2. Okay. Alright. We learned about this and this, 2 days ago, right? What am I supposed to do with these ones? Plug them in. So let's plug it into the left function, plug it into the right function. So plugging 1 in, what's 3 times 1? 3. I leave the thing in the middle alone because that's what I'm trying to if we were squeezing on either side. Okay? The next one is into strength. Okay? But I taught it enough times that I figured out how to make it nicer. Okay? Alright, so on this one here, they told us what they want us to find the limit of. We know we can't plug in the 0 because it's going to make the denominator undefined, okay? I know I can't really use rationalizing. There's nothing in the factors. There has to be some other way to do it, right? So when I'm out of possibilities, that's when the squeeze theorem comes in. So the only thing I know about from algebra 2 and grid, calculus, I know that the cosine function looks like this, right? It's the highest value of the cosine function. 1, right? What's the lowest value on a generic cosine function? Okay, well, we know that it can be stretched, right, and compressed, but for the most part, we know it usually lives between -1 and 1. Alright, so that's where I'm going to start. So I know that I've got this function, cosine, and I'm only talking about cosine. Notice I'm not adding the x squared in yet. And I know cosine lives between -1 and 1. I should have left this. But is that the function they really want the limit of? They want us to multiply that by x squared. So I multiply this by x squared. Those rules of mathematics say I have to multiply everything by x squared. Yeah, so I'm going to multiply everything by x squared. Alright, so now let's look at that. That gives me -x squared less than, I'm leaving gaps on purpose, x squared cosine of 1 over x squared less than x squared. Do I now have functions to squeeze in between? Yeah. So do you see how I worked with what I knew, and I was able to create functions to squeeze? Okay, and those are functions that we well recognize. Okay. All right. Let's go ahead. That's not what we're supposed to put the limit notation on there, right? So I'm going to add that in there. So I'm just put that in the front. Limit as x approaches 0. Limit as x approaches 0. And limit as x approaches 0. Alright, so when we put 0 into -x squared, what do we get? 0, good. And this stuff in the middle, we don't know. We know we can't plug a 0 into it. That's what we're trying to squeeze. Alright, and then when I put a 0 in, what do we get? 0 again. So did we get what we wanted? Yes. What is the limit of that ugly function? 0. Okay, but we have to make a concluding statement about it, so we use therefore. The limit as x approaches 0, x squared cosine of 1 over x squared equals 0. Okay. I know my example number column matches these two presentations that I changed a little bit. Alright, let's look at this one. This is probably the one that's set up most similar to a homework problem. Okay? So I'm going to show you, kind of going to explain a little bit and then have you try it. So it says, use the squeeze theorem, find the limit. They gave us a generic formula for the limit, right? Why do they want me to find the limit as x approaches what? 0. Okay, so you need to set it up. Did they tell you what functions you're squeezing? Yeah, so they've already given you the functions, so you need to add the limit notation and all of that. Go ahead and calculate your limits and then make your concluding statement. So I'm going to give everybody 2 minutes to do that right now. can't even tell you what ECR wants, right? That's our closest one. Right? So we want to try to make sure we all understand the communication. Okay? Alright, that's all I got for you today. You are going to have some time to actually get some work done.